Okay, let's dive right into this. Welcome to This Explainer. Today we're taking a really fascinating journey through one of the most powerful and enduring programming languages ever created. We are going to trace the blueprint of C++, starting all the way down at the low-level microscopic memory, and then we're going to build our way all the way up to the high-level, ultra-safe paradigms of modern C++.
So you might be wondering, with so many shiny newer languages out there, why does C++ still literally run the world? Well, the answer is absolute, uncompromising control. C++ gives developers direct access to the bare metal of the hardware. But, with that kind of power comes a bit of a reputation for complexity. Our goal today is to completely demystify that reputation by building our understanding from the bottom up.
Here's our quick roadmap for This Explainer. We'll kick things off with data types, move into pointers and references, scale up to classes and memory, and finally wrap up with modern C++.
All right, Section 1, Data Types and Precision.
Before we can go off and build complex systems, we really have to get a grip on the primitive building blocks of C++ data. This perfectly sets the stage for understanding exactly how memory allocation dictates the accuracy of our programs. Think of memory like physical storage boxes. A float is a 32-bit single precision box, and it takes up 4 bytes of memory. A double, on the other hand, is a 64-bit double precision box, taking up 8 bytes. So you're essentially trading a little bit of memory size and performance for a massive increase in precision.
And that brings us to a really crucial number, 15. A double gives you exactly 15 decimal digits of precision, whereas a float maxes out at just 7. Why does that actually matter? Well, if you're calculating the exact roots of a complex quadratic equation, using a float is going to introduce these slight rounding errors that just compound over time. Using a double totally prevents those errors. Honestly, it's the difference between landing a rocket perfectly on a landing pad or missing it by a few inches.
Moving on to Section 2, Pointers versus References and Direct Memory Control.
Now we're getting into direct memory management. I know this is notoriously one of the most confusing topics when you're picking up C++, but it is absolutely crucial for unlocking the language's true power. So a pointer is simply a variable that stores the memory address of another variable. Think of it like a treasure map. The map itself is a distinct physical object with its own location, right? But it tells you where to find the actual gold. Because it's entirely independent, you can erase the map and redraw it to point to new treasure. Or it can point to absolutely nothing, a null pointer, and you access all this via the asterisk operator.
But a reference? That is a completely different story. It is merely an alias, like a permanent nickname for an existing variable, accessed via the ampersand operator. Unlike our treasure map, a reference is essentially just another label printed right on the exact same treasure chest. It shares the exact same memory location as the original variable, and once it's assigned, no way, it cannot be reassigned.
So how does this actually play out in practice? Well, pointers are highly flexible. They don't need immediate initialization, they can be null, and they can be reassigned over and over. But that flexibility makes them a bit risky. You could accidentally follow a map right off a cliff. References, conversely, are much safer. They require immediate initialization, they cannot be null, and you don't even need a dereferencing symbol to use them.
Okay, Section 3, Classes and Memory. Time to look at macroscopic structures. We've mastered the microscopic elements, so let's zoom out a bit to the macroscopic level. How do we group all these primitive variables and pointers into structured, complex behaviors? In C++, we do this using structs and classes. While both of them support constructors and member functions, their default security is fundamentally different. It's kind of like looking at manufacturing blueprints. Structs leave everything public by default. Classes, however, are specifically designed to hide and encapsulate private data inside, exposing only specific public members as an interface. This is what prevents external code from messing with the internal engine of your object.
Now, when an object is actually operating, how does it know which specific data it's supposed to modify? That is exactly where the this keyword comes in. Member functions implicitly use this as a pointer to the current object. It's basically the object's way of looking in the mirror, referencing itself to ensure it's operating on its exact footprint in memory.
Next up, Section 4, Object Life Cycles. Birth, life, and death. Because, objects aren't just static clumps of data, they actually go through a distinct life cycle. Step 1. The constructor is called when the object is created, perfectly initializing its variables. Step 2. The object operates within its scope. And Step 3. The destructor, which is marked by that little tilde symbol, runs automatically when the object is destroyed. This is absolutely vital, because the destructor is what automatically releases resources, like heap-allocated memory, ensuring your program doesn't leak memory and just crash. But here is a totally mind-bending fact about an object's life in memory. You'd probably think an object's memory consumption is exactly the sum of its variables, right? Actually, not always. Compilers will literally inject unnamed padding, just empty bytes, into your objects to align data perfectly with the computer's 32-bit or 64-bit architecture. This optimizes CPU processing speed, albeit at the slight cost of memory space. It also supports bit fields, which allows variables to consume even less storage than a standard integral type.
And finally, Section 5, Modern C++ Features, Evolution and Safety.
Let's see how modern standard updates have brilliantly solved those legacy dangers we were just talking about. C++ is definitely not a dead, ancient language. It is constantly evolving. From C++ 11 all the way through C++ 20, the standard has systematically introduced features to make code way safer, far more expressive, and honestly just significantly less tedious to write.
Starting back with C++ 11, we were introduced to the auto keyword and null pointer. With auto providing automatic type deduction, we instantly reduce massive amounts of boilerplate code. And null pointer? That gives us a type-safe null pointer constant, which fundamentally eliminates those dangerous, undefined pointer errors that had plagued developers for literally decades.
And honestly, one of the greatest leaps forward here has to be smart pointers. Just contrast the manual memory management of the past, where you had to manually delete pointers, which so often led to massive memory leaks, with modern smart pointers like std unique_ptr. These enforce automatic exclusive ownership. When a smart pointer goes out of scope, it automatically cleans up the memory. The leaky bucket is finally fixed.
Then moving to C++ 17, we get std optional. Before this, developers often had to rely on risky null pointers or kind of arbitrary default values like -1, just to represent missing data. Well, std optional elegantly wraps this whole concept, safely representing an object that may or may not have a value, right there in the type system itself.
And culminating with C++ 20, we see some absolutely massive additions like concepts and coroutines. Concepts allow developers to constrain template parameters, which, thankfully, makes error messages actually readable. And coroutines bring first-class asynchronous programming natively to the language. C++ 20 really pushes the boundaries, giving developers ultra-high-level abstractions without sacrificing a single drop of that bare metal performance.
So, we've journeyed all the way from basic memory bytes up to these really powerful modern object-oriented paradigms. C++ has evolved from a powerful yet sometimes dangerous tool into a modern, expressive, and incredibly safe language, all while retaining its unmatched performance. So, I'll leave you with this provocative thought. With absolute hardware control at your fingertips and modern safety upgrades backing you up, what will you build with C++? Thanks for joining me on this explainer, and keep exploring.